Hey everyone, welcome to The Rocketeer. This is the second video in a series on OpenRocket. In the first video, I covered the Java runtime file that's necessary to make OpenRocket run. Also, we covered the Rocket Design tab. In this video, we're going to take a look at the Motors and Configuration tab and the Flight Simulations tab. We'll talk about the center of gravity, center of pressure, two things that you need to know to make sure that your rocket is stable in flight. Okay, let's get started. This is the Lock Precision Viper 4 that we used in the last exercise. There's one more thing that I want to cover. In the lower right hand corner, there's a warning. You can't see it on the screen because my window's there, but I'll put it up on the screen so that you can see it. And what it is OpenRocket is complaining about parts that don't fit quite correctly. So the way we fix that is I'm going to go to the nose cone tab and double click that. And this opens up our dialog box. And then there is a box right here called automatic. We put a check mark in that, it magically fixes the whole thing. So we'll go ahead and put the check mark in there, and it reconfigures the fit somehow, and it just it makes the dialog box go away. So we'll go ahead and close that. Now I'm going to look at another file here, open recent, and I'm going to go to the Scorpion. Okay, the Scorpion rocket is dual deploy. It's a rocket I've flown a lot. So we'll take a look at this file. You can see that there's some additional weight added in a couple of these sections. That's fine. And I'm going to go to the Motors and Configuration tabs. So I'll click on that. And there are two motors in there at this point. Sometimes there's motors loaded in the file. Other times it's just blank. I'm going to go ahead and remove those so that we can start from scratch. Okay, so our configuration tab is blank. You go to the new configuration tab right here, click on that, and then you click on select motor. Okay, in this tab we have manufacturer. I'm going to focus on the Aerotech at this point. You can also add others like SDs, Loki, whatever you fly, you can add them. I find it helps just to choose them one at a time. So the impulse I'm going to choose is an H motor. So I'll just slide the slider over to the H. And I don't want to see any 29 millimeter motors. So I'm going to slide this over to 38. Okay, so I'm going to go ahead and take a look at the 123 White Lightning. I'm going to add that. We have to declare the ejection charge delay, which is right here. And I'm going to say just 10 seconds. As a guess. Well, looks like that's too long. So there we go, 10 seconds. I'm going to choose 10 seconds. We'll see how that works. And then I'll choose OK. All right, so we can see that the motor is loaded here. I'm just going to go ahead and add another configuration. Go to the new configuration tab, select motor, and I'm going to choose the H242 also as a 10 second. Okay. And then I'll add one more just for the fun of it. We'll put something a little bit larger in there. So let's go to an I357 and we'll go 15 seconds on the delay just to see how that works. And we'll choose OK. All right, we have our three motors loaded in the tab here. So I'm going to go to the Flight Simulations tab in just a second, and you can see that the flight configuration over here, the I motor is loaded. You can choose no motors or like the H123, and you can see it changes in this area right there. And also the stability changes, and we'll come back to that in just a minute. Okay, so we're going to go to the flight simulation tabs. None of them have been simulated, so I'm going to just shift click all of them, and then I'm going to run simulations. And that happens very quickly. So we can see that the H12310, that the apogee, which is in meters, is 523 meters. We can see that the optimum deploy is about 8.4 seconds. We're pretty close to that, but we could reduce the delay in that if we wanted to, get a little bit closer to it. Also the ground hit velocity, this is how fast the rocket will come down on the parachute. So the parachute's already been selected. If you wanted it to come down a little bit slower, you could change the size of the parachute, and that would change the ground hit velocity right here. Another thing you want to notice is the velocity off the rod. Has to come off the rod at a high enough speed to be stable, and there is no warning here, so we can see that that's in good shape. Now, one of them has a warning. So there's a exclamation point right here on the I-357, and if I hover over it, it will tell me what the warning is. It says recovery device deployment at high speed. Okay, so next thing you want to do is check the optimum delay is 11.8 seconds. So we have chosen a delay of 15 seconds, which means that the parachute's going to come out while the rocket is falling too fast. So we're going to go back and change that. Go back to the motors and configuration, and then we'll choose the motor that needs to be changed. Select motor. And then for the tab up here, I'm going to change that to, what was it, 11 seconds, and tell it OK. Go back to the flight sim, and now all of them will be red, which means that you just need to run all of them again. Anytime you make a change, OpenRocket wants you to run the simulation again. So we'll run the simulations, and there we go. The red exclamation point is gone. All three tabs have a green light, which is good. And so we can double check here. The optimum delay is 11.7 seconds. I chose 11, that's close enough. Okay, so you can go ahead and take a look at this and change a few things as it pleases you, so you can learn about how your rocket will react to different simulations. And it will also tell us the maximum altitude, or the apogee. Under the H-123, it's 523 meters, 570 for the H-242, and it is 891 for the I-357, which means it might be a little bit of a walk for you. Right now we have a stability of 1.95 calibers. So what's a caliber? This is a 3-inch rocket, so a stability of 1 caliber is 3 inches. If you have a 4-inch rocket, the stability of 1 caliber is 4 inches, and so on and so forth. So you want to aim for a stability of at least 1. 2 is fine. That just means the rocket will be quite stable. And so what if we change it to the larger motor? You can see in the diagram here the size of the motor. If we change it to an I-357, you can see that the stability drops to 1.79, which is still stable. However, this is a dual deploy rocket. There is weight in the altimeter bay. The parachute shock cord are also forward, and that tends to create a better stability. Now, the center of pressure is determined by the length of the airframe, how many fins you have, the design of the fins. For instance, if they're swept back fins, the rocket tends to be more stable, and it tends to push the center of pressure back farther. And the other mark here is the center of gravity. Now this mark will move according to how the rocket is balanced. There's some advantages here, like I mentioned before, with the parachute forward. Now this declares the center of gravity as 0.98 centimeters, center of pressure 1.13. So those measurements are from the nose cone towards the rear. But what if the rocket had a much larger motor, or what if it was not dual deploy? Then the center of gravity would be farther back because there would be less weight forward. Well, if that were the case, then we would need to add weight to the nose cone to make it stable. So if the rocket was not stable, that would mean the center of gravity would be too close to the center of pressure. If that was the case, we would go back to the rocket design tab, and then we would select the nose cone. I'm going to double click on that, and then we would add a mass component. So right now our stability is 1.79. I'm going to add a mass component, and I'm going to just change the name of that so we can keep track of it to nose cone weight. And then we are going to add some mass to it. So let's add, we're going to add 20 grams And also we're gonna change the shape of the weight so that it fits properly. So let's pull it back a little bit. So I'm moving the position back. I'm going to increase the length of it and also the diameter a little bit. There we go. And then we'll push the weight more towards the front of the nose cone. So if you were going to weigh the nose cone, add additional weight, that's kind of how it would look. So that's how we're going to modify that. Now before I close it, see we have a caliber of 1.8. Oh, it's already changed it. So it does change it dynamically. So if I go back to the weight and I add more weight to it, you can see it goes from 1.8. If I add more weight, 78 grams brings it up to 1.83. So as we add the weight, you can see the stability change. You should be able to design and build and simulate your rocket and determine if it's stable from this free program, which is great. Okay, till next time, I'll see you later.